Imagine the inequality symbols we learned in algebra class. Those little arrows pointing left and right weren't just about numbers, but about people, power, and opportunity. What if math could give us sharper tools to see the hidden patterns of unfairness in society and even show us how to change them? That's exactly the challenge posed by mathematician, educator, and author Eugenia Chang in her new book, Unequal. She's the scientist in residence at the Art Institute of Chicago and also an honorary visiting fellow at the University of Sheffield in the UK. She's known for weaving deep mathematics with human stories and often asks us to rethink what fairness really means and why simple equality isn't always enough. I'm your host, Autumn Fnaf, and today on Breaking Math, we're going to dive deep into concepts like abstraction, generalization, and maybe even some outliers that help us understand inequality in a whole new way. We'll explore why math, often thought of as neutral or cold, may actually be one of the most powerful lenses for justice. So, grab your coffee, maybe even a bagel, your curiosity, and a notebook, because we're learning about how math doesn't just describe the world we live in, but it can also help us build a more fair and compassionate one. Hi, Eugenia. Welcome to Breaking Math. How are you doing today?
Hey, I'm doing great. Thank you very much for having me on.
Thank you for coming on the show. Now, what inspired you to write Unequal? And while you're here, you might want to elaborate a little bit why on mathematicians are lazy. I'm just going to get you in trouble and say that up front.
Very much trouble, always in trouble. I, in particular, am very lazy, but I like to think I'm not lazy in the sense of cutting corners and not doing the things I'm supposed to do. But what I really like is finding better, more efficient and fun ways to do things so that I can use my brain more smoothly and more efficiently and then get more done. That's what I mean by being lazy. Mathematicians don't like doing the same thing over and over again. It's kind of like you don't want to keep washing each dish individually, so thank goodness somebody invented the dishwasher. And so I like to think math is a bit like dishwashers, except they're inside our brain, where we don't want to keep doing the same thing repeatedly. So we come up with some general theory so that we can do it once, be done with it, and then get on with something else. So that's what I mean by us being lazy. And the reason that I wanted to write this book is because, well, equality is always such an important topic, I think. I really care about the way that the world is fair and unfair to different people. And the thing that really catalyzed it, unfortunately, was a terrible argument that I had with someone about what fairness even means. And I was trying to point out that we were taking different approaches to the idea of treating people fairly. And he just kept saying, you don't get to say what fairness means. Somehow his notion of fairness was correct. Mine was just wrong. And I thought, well, even in mathematics, there are just different approaches to what equality and inequality can mean. It's not rigid and black and white, and there's only one definition. And I thought about all the different approaches that math has that illuminates this for us and gives us ways to think about it. And then it turned into a book in my head. And I thought, well, maybe more people could benefit from this. And maybe I can share this with the world and try to help people navigate these difficult discussions and show some cool math.
Absolutely. I actually have to agree with you, but I'm just going to put this out here. It's the fact that a man said it.
I mean, and it was the fact that he was just so convinced that he was right and that whatever I was saying was wrong, whereas I was prepared to say, well, let's think about the different senses in which these different things could be applicable. We're just taking different points of view. And I always try to say that about math. Math is actually about taking different points of view on the same thing and seeing which point of view is helpful to us and then deliberately choosing that point of view and taking responsibility for having chosen it.
I agree with you. With that, can you also tell us a little bit about your background and your mathematical journey as well?
Yeah, I started out as a traditional pure mathematician. So that's the part of math that appears to be very, very removed from daily life. And I was teaching and doing research in ordinary research universities, having a pretty standard career path as a research mathematician. And then I got disillusioned with it. And I felt like I wanted to help more people get into math because I was teaching math to people who already loved math. And there are so many people who have been put off math by earlier parts of their math education in ways that make me sad because I think they haven't seen what math is really like, or they've been kept out of it by gatekeeping or by the wrong things, tests or memorization or having to do things really fast, which isn't really what math is about. So I really wanted to reach those people rather than the people who already loved math and had been successful at it. And so I wrote my first book, How to Bake Pie, and it did pretty well enough that I was able to step off the normal career path and build myself a portfolio career where I now teach math in a much more unusual setting to art students at the School of the Art Institute of Chicago. And I've written more books. This is my 9th book that is coming out, all to help other people get into math when they've been put off it in the past. I make mathematical art I play the piano, I compose, I do a lot of public speaking. And so I combine so many things that I care about rather than just doing one thing.
Finding what you care about actually is, I think, is the best thing to fuel your career and fuel the future, especially to achieve and inspire the next generation of scientists. Mathematics is just as important as the arts.
Mhm.
And the fact that you are at the Art Institute of Chicago, it's the best place to be at.
Yeah, thanks. And I do think that we really shouldn't pit math and the arts against each other. Sometimes there's a whole, oh, STEM is really important, and then there's a pushback against it saying, no, creativity is really important because STEM is all the things that AI will take over. But that's not an either or situation. And it's really important to show that there is creativity in STEM as well. So I always try to show that there is tons of creativity in math, and math gives us more ways to use our brain creatively, and it gives us techniques for doing that. It's just that it's very often not presented like that in normal education because it's often presented as a series of rules. You just have to follow the rules, and then you either get the right answer or you don't. And if you get the right answer, you're labeled as good at math. And if you don't, or if you question those processes or you ask why, then you get labeled as bad at math. And a lot of my art students say that that's what pushed them towards art because they liked math up to a certain point and then they were bad at it. And so they went towards art. And I'm not saying it's bad to go towards art. It's just unfortunate to label people as good and bad in such a clear-cut way when really there are so many different ways to be good and bad at things and to appreciate things, even whether you're good or bad or something else at them.
So I noticed in the book, you capture math as not just being black and white or good or bad. And the equations actually capture the nuance of this.
Mm-hmm.
So, how can this idea help people see the inequality as much more subtle and accurate?
Well, it's really about seeing inequality as part of equality and that we draw a line in between them and the line can change. It's not in a strictly fixed place. And so, for example, 1 equals 1 is a very, very clear-cut equality. There's nothing different about 1 and 1. So that is a very boring and useless equation. Any equation that we bother saying has some difference between the left-hand side and the right-hand side. Even if it's something really simple like 1 plus 4 equals 4 plus 1. That is a very straightforward equation, and you might just go, oh, well, it's obviously the same because they're both 5. But they're showing us different processes. One is you take one thing and then 4 things, and the other one is you take 4 things and then 1 thing. And there may be situations in which those don't count as the same. Just like when you multiply things, 2 times 3 is 2 lots of 3 things, and 3 times 2 is 3 lots of 2 things. And there are situations where those aren't exactly the same. So if you have 2 packets of cookies, each of which has 3 cookies in, that's not the same as 3 packets of cookies, each of which has 2 cookies in. For a start, one of them wastes more plastic. And there are other situations where, for example, in music, if you do 2 groups of 3, that's going 1, 2, 3, 1, 2, 3. And if you do 3 groups of 2, that's going 1, 2, 1, 2, 1, 2. And those aren't the same. And composers can use that to produce interesting rhythmic features. And the point is that the total is the same, but the way of producing the total is different. And once you start seeing that there's something the same and something different at the same time, you see that there are different choices you can make about whether they will or won't count as the same. And as mathematics goes on to study much more interesting and subtle objects than numbers, it studies things like shapes or arguments or other logical structures, then the place where we draw the line between what counts as the same and not the same is much more changeable. And then we get to make a decision about where we're going to put it, depending on what context we're in.
I agree with that. Now, one thing that, depending on context we're in, you have an example in the book is the number 8 or the infinity sign, and it's topologically equivalent to a pair of pants.
Yeah.
Just the simple things that we don't think about in our daily life. I don't think you're going to want to put a little line that's an 8 on as a pair of pants because the length
Well,
does matter.
yes, so it would be a very, very short, extremely short pair of shorts. And so there, it does matter, right? But topologically, what that means is when we say they're topologically the same, topology is a branch of math studying the shapes of spaces where what we're really concerned with is connectivity. We're not really concerned with length or angles. So in geometry, we're really concerned with lengths and angles and corners. Whereas in topology, we're really concerned with paths. And on a figure 8, you can go, there are 2 loops and they're joined together. And on a pair of pants, there's still basically 2 loops joined together. So the paths you can make through the pair of pants are essentially the same as the ones on the figure 8, but they make very different kinds of clothing.
Yes, exactly. Now, with numbers being powerful simplifications, they can also mislead us when we forget what they leave out. Could you share a couple of examples where we're relying too much on numbers, test scores, and also some obscure real inequalities?
Right. Yeah. So numbers are powerful because they are simple, and they're also dangerous because they're simple. And so they're powerful because it means we can quantify everything. We can line everything up in a straight line and compare them very directly with numbers because numbers fit in a one-dimensional straight line. But that is also dangerous because we have to forget so much information in order to do that. And if we forget the information, and if we also forget that we forgot the information, then things can get really dangerous. And so test scores are a really contentious example because when we have students sit a test, if they just get one number at the end, we haven't really captured anything. We've turned a student into a number and then we're just rating them against each other in terms of numbers, whereas that number might be containing many different types of achievement. So it might be how much they managed to memorize. It might be how just fast they were at writing things down. It might be whether they have a comfortable home in a quiet area so that they could get a good night's sleep before that. It might also be how much private tuition that their parents were able to pay for them in advance. And so there are so many things hiding in there before we even think about the different skills that we might want to test. Because really there are different skills such as understanding, being able to build arguments, being able to understand other people's arguments, being able to recall definitions. And those all get lumped together into a single number, which is just not very subtle. And why do we do it? Well, we still have this idea that we want to put everyone in a hierarchy and rank everyone against everyone else. And we should really think about why we want to do that and why we want to put everyone into a one-dimensional hierarchy, which there are many reasons that knock onto each other because then it turns into how are we going to decide who gets to go to which university? But then there's the question of, well, why should some people deserve to go to one university and some people shouldn't? That's a whole question in there that we kind of avoid talking about when we just talk about whether we should test people or not.
Also, it makes me think a lot more about political debates and
Mm.
where people are arguing at different levels. Do you want to
Mhm.
go into that topic a little bit for us?
Yeah, sure. And that all these arguments and contentious disagreements come from some fundamental different beliefs. It's not that anyone is being, I don't like to sit down and go that some people are being irrational or illogical. What math tells us is that if you start with different beliefs and you proceed from those beliefs, you will build a different world of overall beliefs. And math, the discipline of math, gives us a way of unpacking a world down to its basic starting point so we can see where the disagreement really is. And so, for example, the disagreement might not be about whether everyone has a right to, say, healthcare. The disagreement might be just what is the best way to provide healthcare for everybody. Or some people might really think that not everyone deserves healthcare because they don't want to pay. They might class it as something that everyone should pay for themselves. So then there's a question of what should everyone pay for themselves and what should be provided by society. And then we can see that there are lines we all draw in different places about what we should provide for ourselves and what we should provide as a society. And then we can maybe have a more sensible argument about where we're drawing those lines rather than just saying, no, I don't want to pay for anything for anyone else, when maybe we can agree that perhaps maybe roads, maybe we can't just all each pay for the roads that we use because that would no.
Right. So essentially, whatever metric we're using, you have to be very intentional about those choices.
Yes, and math says that if we start in one place and we build one world, that doesn't mean we're stuck there forever. We're saying this is what happens in this place with these starting points. Here's another place with different starting points where something else can happen. And so, for example, in the ordinary numbers, we go 1, 2, 3, 4, and it keeps going forever. There are other worlds of numbers where you do 1 plus 1 and you get 0. And that's just a different context where sometimes if you do something twice, it's the same as doing it 0 times. Like if you turn a piece of paper over and then you turn it over again, you're back to where you started and it's like you didn't do it. And that's also a slightly different situation from if you push an elevator button and there's that thing where you've already pressed it and you're standing there and then someone else comes along and presses the elevator button like you're an idiot and you didn't press it. You've already pressed it. That doesn't call 2 elevators. It's just the same as having done it once. So in that situation, 1 add 1 is 1. And sometimes some people can get very uncomfortable or even angry about the idea that 1 plus 1 can equal different things. And that's valid. And you might go, oh, that doesn't count. That doesn't count. This situation also doesn't count. Oh, that one also doesn't count. And that is valid, but it's not what mathematicians do. Mathematicians go, that's an interesting situation. Let's study that and see what logical consequences there are to it. We don't just go, oh, that doesn't count.
Now, in the book, you say it's fine to forget the details, but we must remember that we forget them. How can this principle guide us when dealing with everything from policy, data, or even personal decisions when we're dealing with fairness?
Yeah, so if we forget some details and then forget that we forgot them, then we will proceed through life as if those things don't exist, when in fact those things really do exist. Math is about forgetting small details that get in the way of things behaving logically, but we don't forget them forever. We have to remember that they were there so that when we try and apply it back into life, we remember what it was that we did. And so, for example, if we are measuring things, then say because we're weighing things, that when we're dealing with the numbers, it turns into numbers and it doesn't really matter whether it was grams or ounces or pounds. But then when we're coming back into life, it really does matter what those units were. And there are some famous examples in space exploration, I think, where someone was using imperial and someone else was using metric. And that really caused everything to go wrong because they forgot at the level of numbers, it's just numbers, it doesn't matter. But then when you come back again, you really need to remember where it was you started and what the details were that you forgot. And I've done that myself when I'm using a meat thermometer because I moved from the UK to the US, and so I grew up with centigrade and now I'm trying to do Fahrenheit. And if my meat thermometer is set to the wrong thing and I see the numbers going up, and at the beginning it doesn't matter, but at the end it really does, because if you're aiming for, 180 in Fahrenheit and you're waiting for it to get there and it's actually in centigrade, you're going to end up with something very burnt.
I don't think you actually want to have your cake burnt when you're cooking things either.
No, you really
Or
don't.
baking a pie.
No, right.
Now, thinking about that a lot more, you also go into category theory, which
Mm.
is notoriously abstract, yet you liken it to enjoying art without needing to know all of the techniques and technical terms. Now, how
Yeah.
do you hope people actually translate their experiences in mathematics to abstraction, whether it's as art, logic, or even both?
There are a lot of places in the book where I try to reassure the reader all the time that I'm not expecting you to understand all of this. And actually, mathematicians don't understand all of it. But I still want to show it because I think too often we keep people out of math if we don't think they can do it. Whereas there are many other things where you're allowed to go and see things, even if you can't do it. You're allowed to go into an art museum and look at art, even if you're not very good at painting yourself. And you're allowed to go to a concert, even if you don't play any instruments and you don't make music yourself. And I think we should show people math and show how to appreciate it, even if you can't do it yourself. And so I show a lot of things that I am not expecting people to understand. And one of the things I think that's important about math education is realizing that we don't understand everything. And that if you feel like you don't understand it, that doesn't mean that you're bad at math. It might mean that you are seeking deeper understanding. Whereas the people who think they understand it, they're just not seeking deeper understanding because nobody understands it. Mathematicians at the highest levels don't understand it. Every mathematician I know goes around the whole time feeling kind of stupid because we're spending all our time with things that we don't really understand. And so I want to encourage people to feel okay with that. And that's one of the things I love about teaching small children math. And I've written a couple of books for children as well. And I love that because I feel that children are much more comfortable with the idea of not really understanding things because they go through the whole world all the time not understanding things because they're small children. And then adults get a bit freaked out. If you don't understand something completely, you run away. So I put some category theory in there because I want to take people on a journey through to things that are more complicated rather than saying, oh no, that's going to be too hard for you. No, I won't show you that. I want to go, look, here are some things that this is how math happens at high levels so that you can see that it's not about numbers or equations. There's complicated diagrams. I put some in that I didn't explain at all just to go, whoa, look at this thing. And to feel some of that. Or like you can look at a tall building and go, whoa, you don't know how they built it. Or you can look at something like the Grand Canyon and you can go, whoa, you don't know how that got there. I mean, you can start learning. Then hopefully that will pique your interest and you can look at it without knowing anything about it. And then you can maybe feel like learning about the geology of how that canyon was formed. And I started talking about this and I realized I have no idea how the Grand Canyon was formed. So as soon as we get off this call, I think I'm going to look up the geology behind how the Grand Canyon came to be there. And it's just about the idea that math starts with curiosity, wondering how things work, wondering why things work. And category theory is about how things relate to each other. So I think it's not just about what things are equal and what things aren't. It's about other relationships in between. So it really goes into those gray areas in between things being just equal and not equal and saying, what are all the different ways in which things can be related in between just not equal and equal?
If you're thinking about the in between of equal and unequal,
Mm-hmm.
there's a lot of gray area in
Mm-hmm.
neutrality. Is neutrality dangerous? People think of math as neutral or objective, but where does this really play
Yeah.
into effect?
It depends what you mean by neutral. So what I mean about the gray area is that equality is very, very rigid as a concept. And among all the things that aren't equal, there are many things we can say other than just not equal. It's like the fact that if it's cold outside, then that's a very strong thing to say. But there are a lot of ways in which the weather can be not cold, besides the fact that it could be slightly cold, it could be lukewarm, it could be mild, it could be hot, it could be extremely hot, it could be wildly hot, but it could also, it could be raining and it could be warm rain, it could be cold. There's just so many more things. And when we, even talking about something being on a continuum with a gray area, even that is a bit simplified because that's a one-dimensional continuum. Really, there's a whole range of things other than just being equal. Equal is like a tiny dot in a huge sea of different possibilities. And so usually we're thinking about more than just the tiny dot because the only things that are really, really, really equal to things are themselves. Everything is equal to themselves. And that's not interesting at all. So when we're talking about equality between, say, people, then we're not saying that anyone is the same as anyone else because no one's the same as anyone else. In fact, what we're saying is something much more subtle, like how should we treat people? or what role do people deserve to have in society or something. And so once we realize that it's not a very strictly defined notion, then I think it focuses our attention on what it is we're really trying to say and where we're deciding to say that something is not equal. And so, for example, if we say the weather is the same today as it was yesterday, we're not saying it's exactly the same, but there's some kind of range around the same that we've decided to count as the same. And somebody else who's maybe more sensitive to the cold or more sensitive to the hot might go, "What are you talking about? Today is completely freezing compared with yesterday." And so then you can sort of talk about who is sensitive to different kinds of temperature.
Just thinking about the temperature, you also explore fairness with this equality as well.
Mm-hmm.
So, would you like to share how math can actually help us get through these real world contexts like education or justice?
Yeah, there are various things I think of when I think about this. So, one of them is the way we measure how far someone has come. Because if we're trying to evaluate two different job applications, for example, then we're trying to evaluate what someone has achieved up to this point. And some people say, well, we should just look at what they've achieved. But math says if you're measuring distance, first of all, you have to think about where the person started, not just where they are now. And also, there are different ways of measuring it. And so, there's a concept that I introduced in the book, which is quite advanced. So, I enjoyed introducing it. And it's about other ways to measure distance that might take into account, for example, whether you're going uphill or downhill, or whether there's a wind against you, or whether you're swimming upstream or downstream. And those are called metrics. And metrics are any way to measure things that take into account anything you decide. But you have to decide in advance and sort of make it clear. It's like when you're doing math, you start by announcing what it is you're doing so that everyone knows. And it's a wonderful way to avoid ambiguity because then you can't backtrack. You have to really be clear what you're doing. So you decide what metric you're using. And if you're using a metric that takes into account how much people have had support as opposed to how much obstruction they've faced, then I think you come up with something very different. For example, some students who go to university have had to work against everyone telling them that they shouldn't go. Some people come from families where no one has been to university before, where they're skeptical of university, where they say, no, university isn't for you. Whereas, for example, I came from a family where it was basically just assumed that I would go to university. We're not that many generations into it, but still it was just, and I had all my friends basically just kind of vaguely assumed that they would go to university. And so we all had, it's like having a tailwind. It's just pushing with you. Whereas if you fought against it, then that's a whole different set of struggles. And so I think it's a question of whether we should take that into account or not. And it's not about giving people extra help. It's about taking into account the help that they failed to get in the past or the obstructions that they received. Or, for example, if someone has been through their whole education without having a home, if they managed to achieve the same things on paper as someone else who had a luxurious home, a supportive family, and private tuition, then I would be more impressed by the person who managed to do that without having even had a home to go home to, or a house, I should say. I understand that people can be unhoused but have a home, but if they don't have a stable house to go to, then I would be way more impressed by what they have managed to achieve. And I would have amazing ideas of what they might be able to do if they did have a stable housing situation. And so that's what I think of when I think of treating people fairly. No, it's not about treating people the same. It's about evaluating their paths, taking into account a fuller context, which I think is really important. But people can disagree, but then we can have a maybe more sensible disagreement about why we're not taking into account those contexts.
Now, do you see parallels between mathematics and how society actually treats marginalized voices or just these real world scenarios? I've seen this, I'll say I've taught at a community college and 4-year institution. And you just brought up the fact that a lot of students that are unhoused and don't have, even I'll add in the fact that some people don't have the proper mentorship to get to whatever successful metric,
Mm-hmm.
however, we're going to define success.
Mm-hmm.
Do you see some sort of parallel between that?
There are often situations where we're focusing too much on the majority or the middle because practicalities force us to do that. But also, scientific studies do that. They always produce results about some percentage of people being able to do this, or overall, the studies never say everybody. One of my pet peeves is the one that says that physical exercise is good for your mental health. Because of course, it's only good for some people's mental health, and only some physical
Yes.
activity. Some physical activity makes me extremely miserable. And so we have to realize that those things are overall things, and then individual situations are very different from that. And what you say about mentoring is really important, because my experience was that when I was finishing my PhD and applying for postdoctoral positions, I did not believe that I was that great. And compared with some of my maybe male colleagues who thought they were amazing and deserved to have the greatest jobs ever. And it was only because somebody fished me out and sort of made me apply for a much more prestigious job than I would have done. Because I would never, this was when I first moved to Chicago and I had a job at the University of Chicago. I would never have applied for that myself, because I would never have dreamt that I was good enough. But then a professor noticed that I was, and in his opinion, undervaluing myself, and he kind of pushed me to apply for it, and then I got it, and then my career really got going. And so I was definitely the kind of person who needed somebody to push me, because otherwise I would have gone, no, I don't think I'm good enough. Whereas there are other people who think they're great all the time. So it's not about, I don't think that was about giving me extra help. It was about giving me the help that I needed to flourish, and it didn't mean that I was worse. So it wasn't kind of lowering the standards to get me in. It was realizing that I was keeping myself out by not believing in myself. And that's a very crucial difference, because sometimes people can think that it's about lowering standards to let underrepresented people in. And I think it really isn't. I think it's about finding people who've been kept out unfairly and finding people who've been underrepresented, because I think I've accomplished plenty to justify the fact that I deserve to be fished out and that I could believe in myself more.
You're absolutely wonderful, and never undervalue that.
Thank you.
Just seeing the way you think so, I'll say abstractly, and the ability to integrate all of these different topics and make them so understandable to the general population. We need more women like you
Oh,
in the field.
thank you.
We need more abstract thinkers who can pull that in. So always remember your worth. How did someone put it to me one day? Just remember that every successful man always has a more successful woman behind them. So they're most likely riding on your coattails.
You know, when I was younger, I didn't want to draw attention to myself as a woman in a male-dominated field, because I was trying to assimilate. I was trying really hard to assimilate. And I thought, just want to be evaluated on just the strength of my math alone. And it took me a really long time to realize that my math was being evaluated differently because I was a woman. And so when people helped me, it was to counteract that unfairness. It wasn't to give me extra help. And so there are other male mathematicians who got papers published in very prestigious journals, but then they had to retract them because they turned out to be wrong. Whereas my papers got obstructed from being published repeatedly, although there was nothing wrong with them, just because somebody was coming up with some really pedantic objection or just claiming something that wasn't correct. Meanwhile, other people get things published without anyone really checking. And there have even been situations where a referee has objected to my paper because there's an error in somebody else's paper, in a male mathematician's paper, that they only noticed when I referred to the other person's work. So when he published it, nobody noticed it was wrong. Then when I referred to it, suddenly there's an objection. It turns out to be wrong. And that is extremely frustrating. And then I had an experience recently where I was very honored to be invited to give a talk it was a talk called the Distinguished Women in Mathematics lecture at a certain university. They have one a year. And when I was younger, I would not have wanted to do that. And I know that there are female mathematicians who still don't want to because they worry that they've only been picked because they're a woman. And what I want to say is you're not only being picked because you're a woman. You only weren't picked otherwise because you were a woman. You were perfectly good enough. And when I looked at that series of talks, of which one was a distinguished woman in mathematics, every single other speaker was a man. And if there hadn't been one where they were forced to pick a woman, I don't think they'd have had any women. And I also know that I deserved to give that talk. And I think I gave a pretty good talk, and that my work was at least as good, and my talk was at least as good, if not better, than all the other people. So it wasn't that they had lowered the standards to pick a woman. It was that they had finally managed to get over their mental block of inviting women to speak just because they had to pick a woman. And that's very different, but it is a bit subtly different. And in today's world, there is unfortunately not much time and space for subtle distinctions between things. And one of the things I hope is that we can appreciate math as a way to slow down and think through things more carefully, which is why it's such a shame that math is so much about timed tests and having to do things at high speed, because it's like the opposite of what I think math is.
It is the opposite of what math is. Math is to think. It's not
Hmm.
just a knowledge dump. It's thinking about things logically, and
Hmm.
it should never be on time. I
Hmm.
mean, there should be time limits, like 3 days on something really simple. Uh, however,
Right. There are so few situations where you need to do math with a time limit. If it's
yes,
really an emergency, you won't be doing math anyway. It's like the amazing story. I read the book of Sully when he landed the plane on the Hudson. And he had, I forget how many seconds, it was seconds though, wasn't it, to decide what to do after the bird strike. He wasn't calculating, he wasn't doing math at high speed. It was a kind of gut instinctive. I'm pretty sure. I mean, someone can fact check me, but my recollection is that there was something, some very small number of seconds, and the air traffic control suggested the nearest airport for him to go to. And he did not do a calculation because there was no time. He just, on gut instinct, said, I don't think we can make it there. I'm landing on the Hudson. And so, yes, there are situations where you have to do things quickly, but when they are, you're probably not going to be doing math. You're going to be doing some gut instinct thing.
yes. And when in doubt, go with the gut instinct over the mathematics.
Yeah. If that is the situation. And the thing
Yes.
is that one of the things that I try to stress a lot is that math does involve gut instinct as well. And it's about developing your gut instinct so it gets closer to where the logic will be. And when the logic doesn't agree with the gut instinct, it's really interesting. And that's a place where we can then refine both our logic and our gut instinct to get them close together. And I love that. I find it so exciting when there's some situation where my gut instinct seems to be completely wrong. So that can be something that's really scary in life. And that's when people have, that's the cognitive dissonance issue, when someone wants to believe something, but some information is coming in to contradict it, and they can't deal with that dissonance. And so they have to, so what people too often do is they squash out the information in order to stay with their gut instinct. And math gives us an amazing training in going, okay, I'm not going to squash that out. I'm going to really investigate why there is this disconnect. And I'm going to see if I can reconcile those two things and move whichever way will make it reconcile rather than just ignoring some of the information.
I agree with you there. Now, to change topics just a little bit, was there anything that really surprised you when researching this book?
You know, I don't really research books specifically when I'm writing them. What I really do is I've thought about these topics for years before, especially while I'm teaching, because now that I'm teaching art students, it's like a really big part of the target audience. And I give a lot of public talks and I talk to people at the public talks about their experiences of math. So I'm always bringing together those understandings and those experiences so that by the time I sit down to write the book, I've basically got all those thoughts in my head already. And so once I'm writing it, there isn't usually anything that's that surprising because maybe it happened already. It was something that there was something surprising that happened before, and that led to me deciding to write the book in the first place.
That's fascinating. Just thinking about all of the different topics, because you bring in a lot of, I'll just say popcorn topics and examples throughout the book. The fact that there wasn't as much research done, because I know some authors that I've met with, they've taken months to years to write something in comparison. So,
Well,
bravo.
I mean, I started thinking about it in 2019. I started thinking about it. But it really is, because this is my field of expertise, it's really things that I have already been thinking about for so long. But still, there are things I learn along the way that interest me, that often go in, like the story of the reversing of the Chicago River, which is something I learned about actually when I was doing an art installation about the flow of water around Chicago. And so I sometimes do mathematical art installations, and this one was a commission from an art exhibition house in Chicago that was doing a whole thing about water and about Chicago's dependence on water and Chicago's interference with water. And I had heard about the reversing of the Chicago River, and it's called this great feat of engineering. But then when I started learning more about it, it was kind of shocking to me that I better quickly just describe it in case listeners don't know about it already. The Chicago is on Lake Michigan, which is a wonderful source of fresh water. And the Chicago River flows into Lake Michigan. But there's also another river that's quite nearby, which is the Des Plaines River. And the Des Plaines River flows down towards the Mississippi in the end. And so it doesn't actually connect up with Lake Michigan. And the reason Chicago is so well placed is because there's an old portage, which is a raised ground between those two river systems, where Native Americans used to carry stuff to connect the two river systems up. And the native people showed the European settlers that portage to help them because they were helping. And the European settlers, guess what they did? They went, well, I don't want to just carry things from here to here. Let's dig a canal so that we can have huge industry. And so they dug a canal, and then they went, now we could reverse the flow of the Chicago River to take our sewage down towards some other people so that it's not coming to us. They just sent it down the Mississippi. Does the Mississippi want our sewage? I doubt it. But so they used a series of locks so that the sewage of Chicago would flow not into Lake Michigan, but back down there again. And then there were all sorts of unforeseen circumstances, like the invasive carp species that are now swimming up from the Mississippi, threatening to infest the Great Lakes, at which point the natural ecosystem of the Great Lakes is in great danger. And I was fascinated by all of this, called a feat of engineering, because they were so focused on the local effects of what they were doing. They didn't think about any knock-on effects and global effects. And so there's a whole part of the book where I talk about the interaction between local thinking and how if you patch together small parts of local thinking, it can make weird effects on a broader scale. And there's a part of math that I really love thinking about for this, which is where you patch together small things, you can make anything. So it's like papier-mâché or sewing clothes, where you start with flat pieces of material. You can make spectacularly complicated clothes by patching together flat pieces of material. And so you can make twisted things, you can make things with holes, you can make a bagel, you can make a sphere. And so sometimes I have sympathy for the people hundreds of years ago who thought the earth was flat, because all they could see was the part around them where it's flat. I don't have so much sympathy now that there is a lot
I
of
was just
evidence.
going to say that.
Right. But the point is that if you look really close up, it's flat. It could be a bagel. And so there's a chapter called Why the Earth Could Be a Bagel.
Now, for people who don't feel mathy, how can they still use the lessons in Unequal to recognize or resist things that are inequalities in their own lives?
I think the first thing is to try and resist not feeling mathy, and that it's especially important if you have children, because then you are in danger of passing that on to children, because they've shown that math phobia and math fear gets passed down, especially from mothers to daughters, unfortunately. And so it's really important to try and overcome that, and to feel that if you've been made to feel bad about math in the past, it wasn't you, it wasn't your fault, and that someone just should have helped you more. And I'm sorry that somebody didn't help everyone more, but it's never too late. And I strongly believe in this because I got over my sport phobia that I had all the time when I was young. I had an absolute hatred and phobia and past terrible experiences of sport, being terrible at it, being humiliated by it. And I recently got really into playing tennis. And I'm still not good, but I get better every day. And the important thing is to believe that you can get better every day. And it doesn't mean I'm trying to turn everyone into a professional mathematician. I am not going to be playing at Wimbledon ever. Um, but
Says
it
who? Says who?
I'm not going to be playing at Wimbledon. Pretty sure I'm never going to be playing at Wimbledon. And I don't even score or play competitively. I do it to build my physical strength for no particular purpose except for myself, and because I think that that will be good for me as I get older. And so I think with math as well, it doesn't have to be for a job, it doesn't have to be to pass a test. It can be for you to build your intellectual strength. And I hope that everyone is interested in building their brain strength. It's also good for us all as we get older to make sure our brains are active, but it's also good because it can help you understand more things. And so really the first step is to believe that you can build your strength. And so I don't like to think of it as people who are bad at it and good at it. It's just, are you on a trajectory where where you're building your strength? And if you are, then that's wonderful. And as I myself thought when I first went to the public tennis courts and I thought that everyone was going to laugh at me, I thought, well, they're just mean people then. Shouldn't I be celebrated for at least trying to build my strength and get myself some fitness? So it's the same for math. And so I write the books to try and help everyone find a way in. And that I hope if you're curious, my book will help you find a way in. And I hope that you won't feel bad if you don't understand all of it, because I'm not expecting anyone to understand all of it. I don't understand all of it, but I wrote it anyway. And so mathematicians don't understand all of it. I hope that there will be something in there to spark your curiosity and to remind that will make you think of things when you're walking around in your life, because there's such a wide range of topics, life topics that I've included to hope that it'll spark something, even if the story of the Chicago River means nothing to you because you've never been to Chicago. Then maybe the idea of a very, very short pair of pants in the shape of a figure eight can mean something to you because you've had pants that are too short or you want them to be shorter. A very wide range of things for everybody, I hope.
Eugenia, thank you so much for coming on Breaking Math today. And your book reminded us that inequality isn't just a social problem, it's a structural one, and that math can give us the clarity to see it more clearly. You help us rethink what fairness really looks like and how we might move beyond surface level equality to something much more transformative. Until next time, keep questioning, keep learning, and keep breaking down the barriers between numbers and the world they shape.